Let us evaluate the integral 0 to infinity 1 by 1 plus x to the power n whole thing to the power n dx. In fact, we will show that this integral is equal to gamma 1 by n into gamma n minus 1 by n divided by n into gamma n, whereby gamma is well-known gamma function, and then n is any real number greater than 1. Further, we will be needing a number of results, some of them being related to beta function and gamma function. Beta a comma b is defined as 0 to 1 integral of x to the power a into 1 minus x to the power b dx. And there is a relation that says, in fact we can prove it, that integral 0 to infinity t to the power b minus 1 divided by 1 plus t to the power a plus b dt is exactly equal to beta ab. And there is a relation between beta function and gamma function that says, of course there are many other relations, beta ab equal to gamma a into gamma b divided by gamma a plus b. Further, we have recurrence relation for gamma function, recurrence relation for gamma function, gamma p plus 1 equal to p gamma p, and then Euler's reflection formula that says gamma a into gamma 1 minus a equal to pi by sine pi a. Of course, in this case a cannot be equal to integer. Now let's do it. Let's proceed to the proof. Okay, now let's write I equal to integral 0 to infinity 1 by 1 plus x to the power n whole thing to the power n dx. Of course, n has to be greater than 1. Now you see that this is a bit complicated, so we try to simplify it. So we start by trying to simplify it. Let t equal to x to the power n. Okay, now we want to go for substitution of t equal to x to the power n in this expression. So if t equal to x to the power n, then it implies that x equal to nth root of t, or t to the power 1 by n. Let's differentiate both sides with respect to t. So we want to differentiate this expression with respect to t. So d dt of x must be equal to d dt of t to the power 1 by n. Now we know that that's a standard differentiation, that derivative of t to the power a is a into t to the power a minus 1. So dx dt equal to 1 by n t to the power 1 by n minus 1. But you see, we want to substitute dx in terms of t. So from here we can say that dx is equal to 1 by n into t to the power 1 by n minus 1 dt. Okay, now we can write everything in terms of t. Let's do it. So first of all, I equal to since we are taking n greater than 1, so when t equal to 0, x equal to 0, and when x equal to 0, t equal to 0, so this integral will change from 0 to, when x approaches infinity, as n is greater than 1, t also approaches infinity. So integral will change from 0 to infinity. As we said, we want to substitute x to the power n by t, just t. Let's do it. So 1 plus t whole thing to the power n. So we have simplified a bit, but what about this one? What about dx? Dx equal to 1 by n into t to the power 1 by n minus 1 dt. Okay, now we can write this simply as 0 to infinity 1 plus t to the power minus n. 1 by n, it's just a number, it is independent of t, so we just write it outside the integration symbol, and then t to the power 1 by n minus 1 dt. So this reminds us about gamma function. Beta function. This reminds us about beta function. Beta ab equal to 0 to infinity t to the power b minus 1 divided 1 plus t to the power a plus b. Let's apply that result here. Beta ab equal to t to the power b minus 1. Yes, we got t to the power b minus 1. Oh, let's write it once again. We want to apply beta function. So 0 to infinity t to the power 1 by n minus 1. So b minus 1, b has to be equal to 1 by n dt as it is, divided by 1 plus t to the power, we want to write it as b plus 1 plus t to the power a plus b. So we write it as b plus a. We write this expression as b plus a. We got b equal to 1 by n, right? Here t to the power b minus 1. So we got b equal to 1 by n. So this is equal to 1 by n, but we want b plus a, right? So 1 by n. So beta ab is given by 0 to infinity t to the power b minus 1. So 2 to t to the power 1 by n minus 1. So b equal to 1 by n. Then 1 plus t to the power a plus b. So we take a equal to n minus 1 by n and b equal to 1 by n. So this is equal to 1 by n times beta a comma b, right? So a equal to n minus 1 by n, and then b equal to 1 by n. Alright, so we got it in terms of beta function. Next, we know that beta ab equal to gamma a into gamma b divided by gamma a plus b. So let's apply that result. 1 by n we copy as it is. Beta ab equal to gamma a, so n minus 1 by n, into gamma b, so 1 by n, divided by gamma a plus b, so n minus 1 by n plus 1 by n. Of course, where n is any real number greater than 1. Of course, that can be simply written as gamma n minus 1 by n into gamma 1 by n divided by n into gamma n. 1 by n gets cancelled. Now, let's apply the recurrence for gamma function. Gamma p plus 1 equal to p gamma p. So gamma n minus 1 by n, we just need to subtract it. Gamma p plus 1 equal to p gamma p, or that can simply be written as gamma p equal to p minus 1 into gamma p minus 1. So we apply that relation and write n minus 1 by n minus 1 into gamma n minus 1 by n minus 1. But again, if we apply that relation, we'll get n minus 1 by n minus 2. Again, if we apply this recurrence relation, we'll get n minus 1 by n minus 3. Ultimately, we'll be decreasing the value of n, and we'll be writing as, say, we'll be decreasing it to 2 minus 1 by n into 1 minus 1 by n. Of course, this will be only true for n is a positive integer, n has to be greater than 1, g plus, and n is greater than 1. For n belonging to positive integer and n greater than 1, we can write this as n minus 1 by n minus 1, n minus 1 by n minus 2, n minus 1 by n minus 3, and so on. Then 2 minus 1 by n into 1 minus 1 by n into gamma 1 by n. Okay, 2 minus 1 by n into 1 minus 1 by 2 minus 1 by n into gamma 1 minus 1 by n.